Hi, I'm Don Sheehy, and I'm going to give this presentation now on some recent work on something I call one-hop greedy permutations. So a greedy permutation is an ordering on points in a metric space, and you can construct this in any metric space. The idea is quite simple. You start with any point you like to be the first point in the permutation, and then each point after that is the next farthest point. So with a couple definitions we can make this formal. Let's say that P sub I is the first I points in the permutation, and the distance from a point to one of these prefixes is just the distance to the closest point in there. So then the I plus first point will then be defined to be the point that maximizes the distance to the prefix. And if you plug in this definition of the distance, you'll see this is kind of a max-min. In fact, this is exactly the Hausdorff distance. So the distance from the I plus first point to its predecessors is exactly the Hausdorff distance between that ith prefix and the rest of the set. But probably by far the easiest way to get a handle on greedy permutations is to watch it in action. So let's look at a piece of paper here. So here is a set of points in the plane. And what I'll do is I'll just start with any point to start, and then I'm going to look at the distance of all the other points to that one point. And so if I start here, I look for all the distances and I find the farthest next point, and this will be the next point that I add to the set. So I add that one in, and now the next farthest point is over here. And you can see how I can kind of continue this process, and I just draw the line to show you which is the nearest predecessor in the ordering. I can just keep going and selecting points as I go, and that will give me eventually an ordering on the full set of points. Now, one thing you can see is if I were to draw a ball around each of these points whose radius was equal to this line segment, those balls would cover the entire point set. So this is the coverage radius. In fact, that radius is the Hausdorff distance of the sample. And as I continue to add more samples, this coverage radius decreases. So I get a better and better coverage of my data set. And so you'll also notice that even though there are some cases where the points are very close together in the original sample, if I look at just the selected points here that are highlighted, they're all pretty evenly spaced. And so this kind of greedy permutation is really good at giving you something like a uniformly spaced set of points. As much as possible, the points are spread out. And that's why greedy permutations show up in so many different settings. Now, one nice thing about the greedy permutation is that it gives an approximate k-center for all k. Remember that in the k-center problem, you want to find the k points that minimize that Hausdorff distance. So the first k points are exactly a 2 approximation for any k that you choose. So you just take any greedy permutation, you take the first k points, and that's a 2 approximation. But you can't do better than that. So it's NP hard to approximate k-center to a factor that's less than 2. Greedy permutations don't just show up in k-center clustering, but they actually show up in many other algorithms as well. It's a natural way to start things like sparse multidimensional scaling to get a good sample of points. You find these in spanners. It can be used inside proximity search data structures. Personally, I've used these in work on sparse filtrations and topological data analysis. So many cases where these show up. Even though the greedy permutation seems optimal, theoretically, in practice there are a lot of heuristics that work better. And it's not too hard to see why this happens. In fact, some very simple examples show how it's clear in cases which might seem very natural, for instance, points sampled along a line, where you don't really want the greedy permutation. And in some sense, the greedy permutation is a little bit too greedy. I'll show you what I mean. If I have points sampled here along a line, and I'll do a separate example here. In one case, let's imagine that I start at the end with this point. Then the greedy version of this is going to take this point as the second point. And therefore, the coverage radius is going to be something like half the length. On the other hand, I could do better if instead of getting all the way to the end, I kind of back off of the greedy. I go from this point and come back a third of the way to, say, the point around here. And then you can see that the coverage radius goes down from 1/2 to 1/3. Okay, and so we're going to look for a generalization of this idea where you look at what could be the next choice, which would be very greedy, and then you back off of it, right? This is the one hop in one-hop greedy permutations. So one particularly good heuristic that was proposed recently by Garcia-Diaz et al. For the K-center problem is to take what would be the next greedy choice. So for instance, if I have this point in my sample so far, and I would choose this one next as the farthest, what I do is I look in some radius around that point, and I look among all the points in that ball if any of them could do a better job of covering. And that means they cover more points in a ball of the same radius than the greedy choice. And so instead of just taking the farthest point, you take farthest plus this one hop, which gets you to a point, hopefully, that can cover more points. And so this works in the K-center case partly because you know in advance what the radius is. So many algorithms for K-center clustering, they first guess a radius, a coverage radius, and then try to find K points that achieve that radius. And then you could do binary search for the actual radius. We're not going to have that freedom to choose the radius in advance because, of course, with a permutation, you get a whole sequence of coverage radii as you go. But we can still employ the same one-hop idea. So in this paper, I'm going to take that one-hop approach and I'm going to generalize it to the permutation setting. And for us, this means that K is no longer fixed. And this is important because it means that you can't guess a radius and then do some optimization for a particular radius and a particular K and search for the best radius, which is a common approach when you're doing K-center. My goal here is to actually get an entire permutation from this heuristic. So there are some differences. Now, the approximation ratio we'll get is going to depend on some parameter alpha. And alpha really just tells us how much of a neighborhood to look for our next point in. So when I choose my greedy next point, I look in the neighborhood, which is just going to be a metric ball around that point. I shrink it by alpha times the current coverage radius. The main theorem is that if you just take the first K points of this alpha one-hop greedy permutation, you're going to get a 2 over 1 minus alpha approximate K-center. Okay, so you can just directly get approximate K-center. In fact, you can also talk about an approximate greedy permutation, in which case you get a 1 over 1 minus alpha approximate greedy permutation. It looks like, for a bunch of reasons, choosing alpha equals 1/3 seems to be a very good choice. This corresponds to the intuition we get from the one-dimensional case, where choosing 1/3 seems to do just the right thing when it comes to sampling a spoke. Right? If there's a line segment that's densely sampled, you don't want to go all the way to the end. You just want to go 2/3 of the way to the end. And that gives you kind of the best answer in 1D. But also choosing alpha equals 1/3 here is also helpful for the algorithm. It allows you to skip some extra checks. The algorithm itself, to implement it efficiently, we use a version of a discrete Voronoi diagram-like structure that's very similar to one used by Ken Clarkson on some of his nearest neighbor search data structures for general metric spaces. The key ideas that we're looking at are, first, you maintain a neighborhood graph on the inserted points. So the points you've added so far, they roughly know who their nearest neighbors are. Second is you keep track of the reverse nearest neighbors. This is the Voronoi part. Reverse nearest neighbors are the discrete analogs of the Voronoi cells. And then you only make local updates. So every time you add a point, you only have to check using this neighborhood graph which new points have new reverse nearest neighbors. And since everybody knows who their reverse nearest neighbors are, you know who these discrete Voronoi cells are, you keep them in a heap, and then you can quickly find the next greedy point. After you found the next greedy point, you don't necessarily add it right away, you do this kind of local search. If you just do this directly and you don't take one hop, you get an n-log spread time algorithm for computing greedy permutations. Now, our goal is to get this exact same running time asymptotically for one-hop greedy permutations. So we're going to not just blindly take the greedy choice, that is, not just take the farthest next point, but then do this local search and still get asymptotically the same running time. And it's not at all obvious how to do this. And in fact, doing it exactly is still an open question, but I'll show you how to do it with some approximation ideas. So the key to making the algorithm efficient is to not do a full check of all the points in the neighborhood of the greedy choice. Remember that if we were going to look and there are lots of points in here in some metric ball, we would check all of them, and for each one we would see, is this one a better choice? Is this one a better choice? Does this one cover more points at a given radius? On the other hand, if we have 2 points that are very, very close together, one is basically as good as another for covering. That is, if I take one within epsilon away, it will cover the same points if I just increase the ball by a radius of epsilon. So instead of looking at all the points, I take a sample of them, and that sample is actually just a kind of greedy sample of this subset. And I will sample it down to some epsilon radius so that now if that epsilon is a constant fraction of this radius, then I'm only going to have a constant number of points, assuming that the doubling dimension is constant. So if it's a low-dimensional, intrinsically low-dimensional metric space, then I'm only getting a constant number of samples in here. And then in the range samples, I get not just the sample, but what is essentially the discrete Voronoi diagram. That is, I know who the reverse nearest neighbors of all the points are. So from here, I can actually do the range counting. That is, I can count how many points are in a given ball approximately just by counting these points up to their weights, where the weight is the number of points in the cell. That approximate range counting is exactly what you need in order to figure out which point locally covers the most other points. The one-hop time now is going to be proportional to however long it took to do the range search, which is going to only take log spread, because as long as you only choose a constant number of points, you can do this in log spread time using pretty much whatever your favorite hierarchical metric data structure, cover trees, navigating nets, whatever, they all will take roughly the same amount of time. The theorem is that this approximate one-hop greedy permutations can be computed in order n log spread time, because we're going to have this extra log spread term for the range search once per insert, of which there are n of them. So this gives n log spread. Now, there is an implementation available. You can open your terminal and run pip install greedy permutation, and you can find the implementation of this. Python library also includes code for running just regular greedy permutations. That is, there's the naive quadratic time algorithm. There's the algorithm based on Clarkson's data structure that I described. And there's actually a couple other things in there as well, including an implementation of the kth nearest neighbor sampling, part of another paper that I'm also presenting in this conference. So that wraps up the presentation. Thanks so much for watching, and check out the paper for more details, and also check out the code on GitHub. Thanks.